Chapter 4 Energy Sources and Energy Consumption 4.1 Non-Renewable Energy Sources. Let's begin. Our Sun is just an ordinary star. Due to gravitational attraction, the center of its star has high pressure and temperature, which eventually starts hydrogen fusion, and helium is produced. When about half the hydrogen is consumed, hydrogen fusion stops, but helium fusion starts. Successive fusions carry on, or produce a lot of energy, until the core of the star becomes iron. Iron fusion does not occur, or at least it cannot sustain itself, as iron fusion absorbs a lot of energy. Fossil fuels and nuclear fuels are two main non-renewable energy sources that we are using nowadays. 1. Fossil fuels. It is currently the main source of energy. It includes oil, coal, and natural gas. Besides using as an energy source, fossil fuels are also raw materials for organic products, such as detergent, lubricants, and even chemicals. 2. Nuclear power. Hydrogen fusion releases energy. Uranium fission also releases energy. They are called nuclear energy. A. Binding energy. When a nucleus is formed from its constituent protons and neutrons, energy is released as the product nucleus is more stable than the separated individual nucleons. The energy released is called binding energy. A more stable nucleus releases more binding energy per nucleon. On the other hand, to break a nucleus into its constituent nucleons, we have to supply the binding energy it released when it was formed. As energy is released when the nucleus is formed, the mass of a nucleus is smaller than the total mass of its constituent nucleons. The loss is called mass defect, which is the mass equivalence of the binding energy of the nucleus. Binding energy and mass are usually expressed in electron volt and U atomic mass unit, respectively, where 1 electron volt is 1.6 times 10 to the power negative 19 joule, and 1 U equals 1.66054 multiplied with 10 to the power negative 7 kilogram. And binding energy EB expressed in mega electron volt equals to the product of mass defect in U and 931. Which actually comes from the equation E equals mc squared. And note that such relationship is given in the formula sheet in examination. For example, for 0.5 U of mass defect, it equals 0.5 multiplied with 931 mega electron volt of binding energy. So, for a larger mass defect or a larger binding energy, it becomes more difficult to break the nucleus into its constituent nucleons. To compare the stability of nucleus, we have to calculate their binding energy per nucleon, EB over A. A larger binding energy per nucleon means the nucleus is more stable. On page 118, you can see that helium nucleus is exceptionally stable, and iron is almost the most stable nucleus among all. In other words, small nucleus would like to fuse together to form medium-sized nucleus like iron to become more stable. Large nucleus would also like to disintegrate into medium-sized nucleus like iron to become more stable too. Example 1. Which nucleus is more stable? You have to compare the stability of an oxygen nucleus with a uranium nucleus. As a uranium nucleus is so much larger, it has more nucleons, and so its binding energy must be larger. To compare their stability, you should calculate the binding energy per nucleon. After all, an oxygen nucleus is a little bit more stable, as its binding energy per nucleon is a little bit larger. When there is fission or fusion, which usually results in loss of mass, called mass defect, there is energy released. The product nucleus is more stable, and hence results in rise in binding energy per nucleon. In other words, the energy released is the increase in binding energy of the nucleus. Example 2. Energy released in fusion. In this example, helium nucleus is formed when two hydrogen nucleus fuse together. The total binding energy increases, which means a lot of energy is released when helium nucleus is formed. Do check point 1 below.